All right, so the next topic that we're going to be discussing in terms of the dynamic Earth is the topic of volcanism. We're going to talk about volcanoes. Who doesn't like volcanoes? They're things of beauty, of marvel. Societies have created gods and stories and creation myths, all dealing with these things. We've all wondered what's inside of them. Little kids are fascinated by them. If we go to a movie and one's going off in an action sequence, we're amazed by it. We've all seen the films that just, capture our attention. Volcanoes are awesome. So what we're going to talk about today is the study of volcanoes, which is known as volcanism. So our planet is still an active and volcanic one. Any given day, there are 40 to 50 eruptions in some state of occurring, and usually one or two that are beginning. The website that you see in front of you is from the Smithsonian, where they list the weekly volcanic activity. And you can see a list of, 20 or 30 things that are currently going off in different stages. Some of them have been going off for a while, some of them are relatively new. But I'll put this link in the bio down below so that you can track it if you decide you want to. You can also use the USGS website, which will give you some travel advisories, aircraft advisories, and pays a little bit more attention to the volcanoes located within the United States, for example, Kilauea, and the ones along our western shores, but also provides us information for events going on around the world as well. So if we're going to talk about volcanism, we need to define what is a volcano. So we all know what we think a volcano is. We've been drawing it since we were little kids. Mountain with red stuff coming out of it. But we got to get a little bit more technical if we're going to talk about what an actual volcano is. So what is it? So we've got a mountain or a hill. It's usually conical, so it's cone shaped, and it has a crater, an opening, or what we call a vent, through which lava, rock fragments, hot vapor, gas, or other material is being erupted from the Earth's crust, or in the recent past has been erupted from the Earth's crust. Now, sometimes you can have fissure eruptions, and you can have shield volcanoes, which are typically not as steep as a typical what we would think of volcano, but usually that's what we're going to refer to when we're talking about a volcano. Okay, now when we talk about volcanoes, we're usually going to refer to them as either active, meaning they have erupted within the relatively recent past, dormant, which means they haven't erupted in the relative recent past, but they are capable of possible eruptions in the future, and extinct, in which case their lava chamber, their magma chamber has been emptied, and they are no longer a threat to erupt at any time in the near future. So now that we have a working definition of what a volcano is, we should have a kind of working knowledge of what's going on inside of the volcano. Now, a lot of times in the past, maybe you've seen posters that had the insides of these volcanic mountains, and you've seen what is in the inside of them. Perhaps you built one for a school project, but we're going to go through them a little bit and understand that obviously the images that we're going to look at are not exactly what we would see all the time, but what kind of gives us an idea of what is going on the inside. So typically when you're talking about a volcanic mountain, this is going to be your typical structure that you're going to get. So what you're going to have is down here, you're going to have some sort of a magma chamber located well below the surface of the earth. And coming out of that magma chamber, you're going to have a conduit or a pipe. And that conduit allows magma to rise up and eventually reach the vent, which is the point in the earth's crust, which is broken, that allows that hot molten material to come out. The crater is the rock surrounding it. Now, what are you going to have? Understand the big difference. When you have hot molten material inside the mountain, we call it magma. When you have hot molten material coming out, you call it lava. So that's going to be your big first definition that you should kind of pay attention to. We've got your magma down here, your lava over here. Okay, and then as time goes on, you're going to build up layer upon layer upon layer as you have more and more eruptions, and that's why you kind of have this stratified appearance here of different layers. Now, some of it could be lava that's cooled, for example, something like this, like you see right here. Some of it could be ash or cinders or volcanic bombs or all these other things that we'll talk about, this pyroclastic material that builds up on the mountains, and that's going to create different types of volcanoes that we do see in some cases. But your typical standard structure for most volcanoes is going to be this basic vent, conduit, and escaping material. Mixtures of stuff coming out. Sometimes it's a lot of gas, sometimes it's a lot of dust, but there's lots of different combinations which can work. Okay, so here you have a typical what we would call a cinder cone volcano. There is your crater. Your vent would be located in the center, and all this material is material that has been ejected from this and has collected around this particular vent. Okay, here you have a crater right here with a actual lava lake inside of it from the people at National Geographic. Okay, very beautiful image. Okay, and you can see the lava here just pooling along with the vapor and the different gases coming out. Okay, and here you have smaller little parasitic cones on the side of this greater volcano, these smaller little vents that will allow material to come out. Sometimes they could just be steam vents, which we call fumaroles. Okay, and there are a lot of different independent structures that we could discuss, and if you want to learn about, I'll put a link to the National Geographic site down below where you can learn a ton about these, more than your teacher would have you learn for this class. So now that we've talked about magma, or at least mentioned it, let's talk about where it comes from a little bit. So remember, when we're talking about magma, we're talking about molten material that is below the surface. It has not yet come out. So where does it come from? So magma primarily comes when you get the partial melting of either periodotite or basalt beneath the earth, and it partially melts and forms a liquid substance that we call magma. Okay, now this liquid substance, having a lower density than the stuff around it, is going to rise up, and it's eventually going to form a kind of like magma pond or magma reservoir in the lower crust, and it's just going to sit there. If, for example, you get that magma pond, so here you see in this image right here, you have the asthenosphere right there, you have the partial melting of the upper portions of that. Since it's now in the liquid form, it's going to have a lower density, and so what's it going to do? It's going to rise up, and it's going to pond, and it's going to form this big area right here, okay, where you get kind of a ponding effect. Okay, little blobs of that are going to slowly ascend once again because they have lower density, and they're going to form a magma chamber. Now, if any of these two structures doesn't find a crack or a hole, it's just going to stay there, and it will stay there, and it can stay there for millions of years. Slowly over time it'll cool. Differentiated cooling might lead to different minerals. Okay, you might eventually have some uplift where that material gets lifted up and you can harvest it as either granite or various other materials that we use for industrial purposes or jewelry purposes or things like that. But if you do happen to find a break in the crust, you'll form a conduit. And that conduit, like we said, will lead up to a vent, and eventually you will get the eruption of your particular magma. So once again, you start down here, and it's all because of differences in density that this material slowly rises and rises and rises and rises and rises. Now, this is not to say that this is always the same and exactly occurs in the same way, with the same force, with the same eruptive nature. There are a variety of different types of eruptions that can and do happen on the surface of the Earth. And so when we're talking about volcanic eruptions, we do have to talk about the different nature of eruptions that we can have. Basically, what we're talking about, is it violent, is it not violent? Is it forceful, is it quiet, is it gentle? Okay, and whether you get a violent eruption or a smooth eruption primarily comes down to, well, what's inside that magma, what's inside that lava. Okay, basically we're going to be talking about what's the mineral composition and how much material is dissolved within that lava, what we refer to as the volatiles. A high amount of volatiles can lead to a very violent eruption. A lower amount of volatiles can lead to a lower intensity eruption. You're also going to talk about the thickness of the lava and the thickness of the magma. Those things are all going to combine to give us different types of eruptions. And so you can get eruptions where they're incredibly violent, or eruptions where they're relatively gentle. So for example, here you have a volcanic eruption occurring in Hawaii. And while you go, oh my God, there's a big fountain of lava. Yes, but look at the area around this. You have very minimal gas, and most of the lava is just kind of easily streaming out here. It's such a low violence, so low energy eruption that you can actually have a helicopter that's buzzing around this with minimal danger, as opposed to something like this, which looks like something out of the end of the Bible, where you've got fire and lightning and smoke. This looks like something's going to come out of it. Some sort of Marvel villain's going to come marching out of the sky. This, not so much. And the main difference between these two is exactly what is inside that material that is coming up out of the vents. So when we talk about magma composition and we talk about how it affects its properties, we got a kind of easy, basic little chart that we want to look at. Okay, so you have different types of compositions for magmas. You have what we call mafic, intermediate, and felsic. Now these should all be terms, depending on what teacher you had, that you've seen in your geology lesson in your earth science class. So when we talk about mafic, sometimes we refer to that as basaltic. Okay, why? Because typically the rocks that are going to come from that are going to be basaltic in nature, so your basalts and your gabbros and things like that. Your intermediate compositions, or what we call andesitic, because that's going to be like your andesites, okay, and diorites and things like that. And then your felsics, which are going to be rhyolitic in nature, and this is going to be things like rhyolite or granite or things like that. Okay, and so when we're looking at these, okay, what are we talking about? One of the big things we want to talk about is how much silica. Remember, we talked about silica earlier in the mineral compositions. We'll put a link up to that in the upper right-hand corner of this video. We'll also put a link down below to the video, the mineral playlist that we were talking about. But when you're talking about silica, so silicon and for oxygen, how much is in there? Okay, mafics have the lowest amount of silica, felsics have the highest amount of silicas. Okay, this can also lead to the thickness of the particular material that's coming out. The thicker it is, that's going to be a problem. That's what you see right here in this viscosity. Viscosity is how it flows. So, okay, high viscosity means it doesn't flow very easily. Low viscosity means it flows quite easily. So think of like water versus cold maple syrup. Okay, if water, if you have a lava that's flowing like water, it comes out really easy. It's not a problem. If it comes out like cold maple syrup, you gotta put, maple syrup in the refrigerator, you try to pull it out, it's thick and it doesn't come out easy. That's going to be a problem because that can easily get stopped up in the conduit, in the vent, and create all sorts of explosive reactions. And finally, you have the gas content. Basaltic magmas are going to be between 1 to 2% gas. We'll talk about what those gases are in a little while. Andesitics are going to be between 3 and 4%, and felsics are going to be between 4 to 6%. And so if you're looking at these, your felsic eruptions are going to tend to be the most violent, your mafics are going to tend to be the more gentler ones, and then your intermediates are going to be intermediate. Kind of appropriate titles for all these things. So it should make a lot of sense if you want to be able to follow this. Once the magma has escaped through the vent, now we refer to it as lava. Luckily for us, these lava flows still keep the same basic names as the types of magma. So we still have felsics and mafics and andesitics, or the other terminology, intermediates and basaltics and things like that. So the first one we're going to talk about are going to be basaltic lava flows. Now, basaltic lava flows are going to tend to have a relatively low amount of silica. They are going to have a relatively higher amount of ferromagnesium metals. That's going to make them a little bit darker once they cool and things like that. But having a very low silica content does not make them very viscous, which allows them to flow relatively far and fast. Okay, and we give them the name obviously because when they cool, they turn into basalt. Now, when we have basaltic lava flows, typically, not always, but typically there's two main types that flow. Now, the terminologies that we have for this may sound a little strange to you because they're not typical Western terms. They come from the state of Hawaii and the native people to those islands. And so the types of flows we have are what we call a'a and pahoihoi. I hope I pronounced those correctly. If I didn't, please feel free to correct me in the comments below. But they look dramatically different, although they have the same basic material. There's a couple of reasons behind it. If you want to know, we can get into that perhaps in a later video. But flows tend to be a little bit chunkier. The rocks that tend to form from that tend to have a little bit more of a jagged appearance. They tend to almost like make a clinking noise as they tend to flow. They tend to be sharper edged and things like that. So both of these would represent an active flow and then a cooled flow below. Pahoihoi flows tend to have this much smoother appearance. They tend to have this almost like skin of rock that cools along the top of them. And when they cool, they tend to get this rope-like appearance. It's very, pretty sort of almost like sinewy texture that you tend to get from these. You also can, occasionally get material that's ejected from these, particularly lava blobs or that get shot out and turn into bombs and things like that, that have a high gas content. When these cool, they'll typically turn into rocks like this, which would be scoria. Scoria is an example of a vesicular igneous rock, and it's called vesicular because you can clearly see in the image there are lots of little holes. It almost looks like a sponge. These were all previously filled with gas. As this rock cooled, as it hurtled through the air, the gas escaped due to the pressure differences, and the rock cooled very quickly, leaving the impression of all these little gas pockets that you saw in here. So this would be an example of a scoria. And so in the image here, you can clearly see the difference between these two lava flows. Here you have a pahoehoe flowing nice and smooth. You can see the rope-like appearance here. And here you have the much rougher, slower, clinkier, chunkier flow that you would have. So this is what we're talking about with the difference between these two types of basaltic lava flows. Now, sometimes when this lava flows, when it works its way from a volcano, it can actually form tunnels or paths beneath the volcano. So the next type of lava flow we're going to talk about is going to be a andesitic lava flow. Andesitic lava flows, or intermediate lava flows, are going to be primarily found in the Andes Mountains, which would be on the western coast of South America. And these are going to be slightly lighter in color due to a lower ferromagnesium count and a higher silica count. And a lot of these are going to tend to break down and make absolutely wonderful agricultural soils. Basaltic lava flows can be the same thing, but these can turn into very, very rich soils, which will provide a lot of nutrients and a lot of minerals, which is one of the reasons that a lot of the countries in these regions can make absolutely wonderful crops. For example, coffee in Colombia and places like that tends to grow on the slopes of former volcanic, or in some cases active volcanic slopes, and that soil gets rejuvenated by these lava flows and can produce very rich crops which are very nutrient demanding, such as coffee. The last type of lava flow that we're going to talk about are going to be rhyolitic flows. Rhyolitic lava flows are going to be much higher in silica content, much lower in ferromagnesiums, leading them to have a very light color. Okay, we found these all across the planet, but we do find them a lot along the western United States. We find these massive rhyolite fields, such as the one pictured in the image below. You can see it has a much, much lighter color as compared to most of the other lava flows that we have been looking at, and this is due to its relatively high silica content. There are some unique lava flows that exist in the world, unique because of the way they look or the colors they present or things like that. And one of these would be the lava flows of the volcano. I'm going to try not to screw this up. I apologize if I screw up the pronunciation. Kawah Ijen in Indonesia, which has an incredibly high sulfur content. This incredibly high sulfur content leads to the lava having a unique purplish color like you see in the image here. And in fact, to this day, there are many villagers that live in the area around here that do the incredibly dangerous job of going in there during the daytime and pulling out the sulfur, which can be used in a variety of things, such as fertilizers and things like that. And so the image that you're looking at right now is actually the volcano itself, and you can see the bluish purplish color coming off as these particular lava flows escape from this volcano. If you ever get a chance to go to Indonesia as a tourist, this is an absolutely beautiful thing. I'd love to go there myself and be able to see this. Definitely a hope for the future. So not all the material that comes out during a volcanic eruption is lava. There are various different things that do come out. There's obviously the gases, which we'll discuss in a minute, but there are some other solids that are ejected during a volcanic eruption, and we call these pyroclastics. Now, the word pyroclastics literally means fire fragments. These are chunks of material that are expelled during a volcanic eruption and can either stay suspended in the air for short periods of time or rain down as the proverbial hellfire that you have heard of before. When we talk about these different fire fragments, we break them down based on their size and where the material came from that is being expelled. So we have what we call volcanic blocks, we have what we call volcanic tephra, and we have what we call a pyroclastic flow. And we'll talk about each one of these in particular and describe what it is and the sizes of the particles and where they come from. Give you a couple images in a second. And so when we're talking about volcanic blocks, what we're actually talking about is chunks of the cone around the volcanic vent that gets shattered and broken during an extremely violent eruption. And this extreme energy causes these broken pieces to fly away from the vent and land at some distance away. Now, depending on the strength of the eruption, there's obviously going to be a difference in distance as to where these land. So in this image that you see right here, you actually have a volcanic block and you have a rock hammer right here for scale, and you got to figure that's about probably about a half a meter for the rock hammer, so that you're talking this is going to be at least 3 feet or a meter across and probably meter and a half this way. Imagine how heavy that is. You're talking a lot of energy to move this. Now this is going to be relatively close to the vent, but you can get them knocked away very, very far. This right here is a volcanic block that on the Pacific Northwest of the United States, expelled by the volcanic mountains that we have along our western shores. This is located right next to the ocean, and so you have to figure this traveled a good chunk of distance away from where it was originally a part of the mountain. So the next thing we're going to talk about is what we call volcanic tephra. So volcanic tephra are solid particles that are shot out during a volcanic eruption. And there's lots of different sizes that can get shot out. Some of them stay aloft and some of them come down like we discussed before. So how do we tell the difference? Well, we tell the difference by diameter. Obviously, these particles are going to be different in size. So if you have something that's less than about a thousandth of a millimeter, we call that volcanic dust. If you're a little bit bigger and you're less than about 2 millimeters in diameter, we call that volcanic ash. If you're between 2 to 64 millimeters in diameter, we call it volcanic cinders or lapilli. And anything bigger than that, we refer to as volcanic bombs. Now, volcanic dust can be very, very fine, and sometimes, based on if it gets caught up in the airflows and the air currents, it can spread over a wide distance. And sometimes we find this volcanic dust at huge distances away. We've found volcanic dust from eruptions in Indonesia, in the African nations of Malawi, and things like that. We have discovered this in the Arctic and this Antarctic, trapped in glaciers from volcanic eruptions that happen at a great distance. So volcanic dust can travel very, very, very far. Volcanic ash, like what you see on these cars right here, obviously won't travel nearly as far, but it can travel a decent distance away from a volcano, and it can present certain problems. When it lands, it can be incredibly heavy, particularly if it mixes with water, and it can turn onto almost like a cement. And if this lands on the roof of poorly constructed structures, it can cause devastation. The roofs will cave in, and that can cause a loss of human life and property and things like that. And unfortunately, it does happen, particularly, like I said, in regions where you have substandard construction around volcanoes. If volcanic ash gets caught up inside of combustion engines, it can gunk up the engines as well and cause them not to work as well, and that can be a problem. And finally, if volcanic ash gets breathed in, it can cause all sorts of problems to living creatures like humans. Like I said, when it mixes with water, what can happen is they can effectively turn into like a cement, and that can be incredibly damaging for your lungs. You'll effectively drown in volcanic ash, which is not good. Secondly, what you're actually breathing in is ash like we would think of like coming out of a fire, but they're very small pieces of silica and they're almost like glass. And so what they'll do is they'll irritate your throat and they'll tear it up, and they'll irritate your eyes, they irritate your nasal passages, your throat, and they can cause a lot of damage that way, which is why if you're ever caught in an area where there's a volcano going off actively, you should try to cover up anything, any parts of your body that have mucous membranes and things like that. um, Scientists typically wear goggles and masks and things like that. When we're talking about things like cinders and lapilli, you're talking about here you have your little bits of material here. Now, obviously, when this comes down, this can feel almost like birdshot or buckshot if it was hitting you from the sky. You've seen movies where volcanoes go off and you hear the little things hitting. They sound like beaties. This can be quite dangerous. Now, they're small. Here you have a dime for comparison. But imagine getting hit by this. That would not be good. Once again, also, if this lands on roofs and things like that, this is little bits of rock. This can definitely cause cave-ins and roof collapse and things like that. And finally, when you have volcanic bombs going off, just an absolutely awesome sounding term, by the way. Basically, what you have is you have material here, and you can still see how it's glowing down here. That kind of like insta-cools and it comes down. And sometimes people have been around, they've actually reported that there's almost like a whistling noise that comes from these, and that's basically the gas as it's escaping and traveling through the various vesicles and pathways, and they'll basically come down and they'll make a high-pitched whistling noise. I won't make it right now because it would really hurt your ears, but it can be quite deadly, and then they'll hit the ground and they might still be molten on the inside, and so you can get some like splatter coming out of them. It can be quite dangerous. It can set dry brush like you see here on fire as it rolls down, so they can be quite deadly. Obviously, once again, if these were to hit a roof or a car or a person, lots of damage, injury, and possibly death. And then once they cool, you can see them here, and you can almost tell how this was like molten when it was flying out of the air, and then as it flew out of the air, it cooled, and you can almost see that streamlined appearance as it was flying through the air. And once again, there is a coin for reference sake. What you're seeing here is obviously an image of these volcanic bombs being produced. So you can see the lava being expelled here. It goes to the air. It's going to insta-cool. or cool quite rapidly, and so you're going to get your, depending on what it is, your scorias or your pumices or your obsidians or things like that. You're not going to get a lot of crystallization because the cooling process is going to be relatively quick. That happens in these cases. Finally, the last thing we're going to talk about, and some of the most devastating and interesting aspects of volcanic eruptions, are what we call pyroclastic flows or nube ardente. I probably said that wrong. I apologize once again. So, when you get a lot of ejected material coming out of a volcano, and that mixes with the superheated gases, it's going to get forced up into the air quite rapidly. But eventually, gravity is going to win. And when gravity wins, it's going to pull it down, and it's going to pull it down the slopes of the volcano. Now, the problem is those superheated gases can almost create like a cushion between the material and the sides of the volcano, which minimize friction and allow it to race down the side of the volcano quite rapidly. And this can cause all sorts of untold devastation, particularly for people who happen to be researching or on the sides of a volcano, and can be quite deadly. Some of the worst deaths that have happened because of volcanic eruptions have been because of these massive pyroclastic flows that have existed. So basically what you have is you have this volcanic eruption, so all this material is going to get forced out and up here. But like with most things, gravity is eventually going to win. When gravity wins, it's going to pull it down, and that material is going to come flying down the side of the volcano here, and anything trapped in that path is going to be caught in this mixture of tephra and superheated gas. It can cook you alive. It can burn you, obviously. It does all sorts of horrible things. It can suffocate you. It can asphyxiate you, subject you to toxic gases and things like that. Being caught in a pyroclastic flow, kind of like this image, not a good thing. It's not a place you want to be. Okay, and we have in fact seen many historical cases where this happened. For example, in the cases of the people of the town of Herculaneum and Pompeii, two towns on the slopes of Mount Vesuvius, located not too far from the city of modern-day city of Naples. This is one of the most famous volcanic eruptions to ever happen in the first century AD. The individuals in this town were caught unawares, and to this day we have found several of them encased in volcanic ash when they were rediscovered, because the entire town was covered when they were rediscovered. Plaster molds were made of the voids where their bodies used to be, and we have been able to actually see some of these people in their last moments. And so here you have a particular event. You have two individuals and a small child. I know it's sad. Um, Here we have an individual in one of the cases in the museum that's right there, and you can actually see a close-up here of this individual, and their body was encased within plaster, and you can see that this was, a quite dramatic and quite sudden death. There are many movies on this, many documentaries very well made on this. And so here's what one would actually look like. So you can see it erupts, and you can see the material racing down the side there. Okay, and being caught in that would not be a situation where you would want to be caught in. It would not be a good recipe for a relatively long life expectancy. And yet again, another quite dramatic effect that can happen during a volcanic eruption is what we refer to as a lahar. So a lahar is basically the combination of a pyroclastic flow and a large amount of water. So when you get a pyroclastic flow and it combines with a large amount of water, you can form these mud flows that we call lahars. Now sometimes you can just get a lahar when you have a volcanic eruption and it melts a huge amount of ice that happens to be sitting on top of a volcano that mixes with the dirt and the soil and just creates these mud flows. But when they're mixed with pyroclastic flows, they tend to be even worse. A good example of this happened in this location. This is a mountain in Colombia called Nevado de Ruiz. And in the 1980s, this mountain erupted. And when this mountain erupted, all that ice that you can see along the top there obviously is going to melt quite rapidly and flow down the sides of the mountain. Problem was, there were towns located relatively close to this volcano. One of these towns was a town called Armero, and that town became inundated with mud. You can see it here, several feet thick. It killed several people. Um, One famously young girl who became kind of the image for this. I won't include the image. You can look it up, but it is a little bit unsettling, certain aspects of the image. But this town was just completely inundated. If we look at the town today, this is what's left. They have since cleaned it up, but the town has been abandoned. The town sits there, it's abandoned, it was full of people, farmers, individuals who were living their lives, and it was basically wiped out. The scary part is if we look at the mountain today, this is what the mountain looks like today. Once again, it has a fresh snow cap and it's still smoking, and there's still other villages in the area which could be a problem. Now, to give you an idea of how dangerous these events can be, what we're going to show you next is an actual image of an actual lahar actually occurring. And so here we have the image of an actual mud flow flowing. This is in Indonesia. We have all this mud coming down a pre-existing river channel and basically overflowing a road and a bridge there. And just imagine the devastation and horror of this coming towards your town. This is what engulfed that town of Armero and wiped out many of its populace. Now, finally, the last thing we're going to talk about is gases. We've talked about how they are a major constituent of what comes out of volcanoes. We've mentioned them, but we haven't really talked about them. And so what are we talking about? Well, what we're talking about is the dissolved gases that are held in molten rock by confining pressure. Okay, big fancy sounding word. What does that mean? As rocks descend into the earth, they're going to carry lots of different materials with them. One of the primary materials, particularly if you're talking about plates by subduction zones, is going to be water. Water is going to get trapped in the sediments. Those sediments are going to be saturated. Their pores are going to be filled with water, and they're going to get pulled down into the earth. As they get pulled down into the earth, they're going to get heated up, and you're going to have these different amounts of pressure. Now, sometimes this pressure can just hold that water inside the rocks and nothing really happens. But as that rock melts and ascends and finds things like conduits and magma chambers, different amounts of gas can kind of bubble out and form in these particular magma chambers. And so what we find when we look at the gases that are eventually released, because what happens? The magma fills up with these little tiny bubbles, and it's not a big deal until it finds a conduit to the surface. Eventually those little bubbles are going to join out and make bigger and bigger bubbles, and depending on the type of event that we have and the type of volcano that we're talking about, you might get an explosive eruption, which would be similar to like shaking a can of soda. That's the easiest way we can kind of imagine what these gases are like. They're like the little bubbles inside a can of soda. As long as the can remains sealed, you can't really see them. But the second that you open up those can, the bubbles are going to try to escape. Now, if you shake up the can, we obviously know what happens. It's going to explode out and be much more violent. That's basically what happens with magma. It's very similar to the soda can analogy that I just described. Now, the primary gases that we're going to have in this volcanic soda can are going to be water, carbon dioxide, and hydrogen sulfide. You're also going to get some sulfur dioxide and a mixture of other gases as well, carbon monoxide, nitrogen, ammonia, depending on the particular volcano, they might be different from place to place. But these are going to be your primary constituents of volcanic gas, or what we would refer to as our primary volatiles released during outgassing. Outgassing being the process by which volcanoes let this go. Volcanoes are actually some of the largest producers of carbon dioxide in the world. So typically what will happen is you'll get a volcano and it'll just pump out gas like you see in the image located on your screen right now. And so this material will puff its way out. It's not always an indication of an active eruption. Sometimes this is just a material escaping as once again it reaches that surface and you have the difference in pressure between the confining pressure below the earth and obviously the atmospheric pressure, which is much, much less. But sometimes you can also get a violent eruption where it violently will push its way out. There are different types of eruptions with different levels of outgassing and violence and things like that. All these would be, obviously different uh, factors affecting these sorts of things to going on. While outgassing is a perfectly natural process, and normally it has very little effect on human civilization and the biosphere in general, there have been times in our history where it's had a catastrophic effect. One such example of this was in the African nation of Cameroon in 1986. In that nation, there was a lake by the name of Lake Nyos. Now, Lake Nyos was a relatively benign looking lake sitting at the top of a mountain that most of the natives in the region thought very little of. It was a pretty lake, but nothing major. But in 1986, in August of 1986, it went from looking like this to looking like that. Now, this second image does not include a filter. I did not touch up this image. This is what the lake actually looked like. So what caused it to go from that beautiful blue lake to this weird pinkish color, and how could that at all affect humans? Well, I'll tell you. So what ended up happening is that this lake was actually sitting in a caldera. A caldera is a collapsed crater around a volcanic vent. Now, that volcanic vent still had chimneys, and those chimneys were still pumping volatiles into the water. Now, these volatiles primarily consisted of carbon dioxide, and that carbon dioxide kind of sat in a layer at the bottom of the lake innocuously, not doing a whole lot of stuff. But this region of Africa is known to suffer from earthquakes and volcanic eruptions. And sure enough, an earthquake occurred. When that earthquake occurred, it triggered a landslide. That landslide disrupted that layer of carbon dioxide at the bottom of the lake and caused the carbon dioxide to rise and burst out. Now, being that carbon dioxide is much, much heavier than air, it hugged the ground and went right down the side of the mountain and nestled in this valley down here. When it nestled in this valley down here, that carbon dioxide asphyxiated almost the entire town. Now, when this happened, it was in the early morning, and so most of the villagers were asleep. And so most of them just died in their sleep. And it wasn't discovered until some individuals from a nearby town were coming to visit some of the towns around here, and they took note that everything was quiet, like eerily quiet. There were no insects, there were no animals, there were no birds. Nothing was making noise. And when they walked into the town, they found hundreds of people just dead, livestock dead, all over the place. Okay, and it was that they had been asphyxiated. And so later on, there were images taken from helicopters and things like that, and we saw things like this, where you just had this whole herd of cattle that just all were asphyxiated and passed away. Okay, and it just wiped them out in an instant. Relatively silent death, but it resulted in a large percentage of people, almost 2,000 people, passing away. So ultimately, what we discovered is that Lake Nyos released about 1.6 million tons of carbon dioxide, and this is what led to the death of around 1,800 people and around 3,000 cattle. And to this day, we still monitor Lake Nyos along with two other lakes in the region in order to prevent such events from happening. And one of these lakes, Lake Kivu, which sits in the Democratic Republic of the Congo, contains a large amount of methane, which could also be problematic to the individuals living around the lake. And if this large bubble that was located here were to be released, it would once again cause the death and devastation of a large amount of people. And so we are currently trying to discover ways in which we could remove the methane from the bottom of this lake so that an event and tragedy such as that of Lake Nyos does not occur again. Yet another after effect of a volcanic eruption that can occur is the very well-known tsunami. Tsunami, obviously coming from the Japanese, is a word which literally means the seismic sea waves that are created during earthquakes or volcanic eruptions. And when this happens, the amount of energy that's released can cause landslides, which reach the ocean and can cause these massive waves to be generated. And these massive waves can cause all sorts of devastation and destruction. Now, sometimes you can have this because you get an undersea volcano erupting and it causes an undersea landslide and it'll generate these massive waves. And if there are, lands located around those waves can stack upon each other and create these big waves like we saw in Japan in 2011 and during various other events. Basically, what happens is you get a massive volcano happening, going off here, massive volcanic eruption like you see here. Okay, a bunch of material is expelled laterally. You get a pyroclastic flow or just a massive landslide. This landslide goes into the ocean. It generates, a pulse, and this pulse is going to race out across the ocean and can devastate distant coastlines. This can be quite damaging and quite devastating. And so whenever an eruption happens anywhere near the coastlines, anywhere, particularly around the Pacific Rim of the Earth, we pay particularly close attention because these waves will radiate out in a circular pattern and can cause devastation many, many, many hundreds of miles away. And for example, this has happened in the recent past. For example, in January of 2022, an immense eruption happened in the South Pacific at a volcano which is known as Hunga Tunga Hunga Hai Pai. Once again, proudly butchered that word. But this eruption was so powerful that we were actually able to see it from space, which is the images that you're seeing right now. And the blast wave that was produced by this radiated around the planet and generated massive tsunamis and tsunami warnings all around the Pacific Ocean. Okay, this event was incredibly energetic, and scientists are still studying it to this day. I'll put a link down below to some videos on this and some documentaries about this that were really, really, really well done. So now that we've talked about all these different types of eruptions, well, we got to figure out a way to measure them because we're scientists. That's what we want to know. We want qualitative and quantitative data. And so what we've created is what we refer to as the VEI, or the Volcanic Explosivity Index. Basically, it's a measurement of the amount of power that's given off during a particular eruption. Now, this is a logarithmic scale. So what does that mean? It means it's based on powers of 10. So when you go up by a number, you're not going up by one, you're going up by tens. So it's like saying 10 to the second, 10 to the third, 10 to the fourth, 10 to the fifth, etc., etc., etc. Okay, so something that is three units higher on the explosivity index isn't 3 times as big, it's 1,000 times as big. Okay, just kind of give you an idea of what we're talking about. And so what we're measuring is the amount of material that gets ejected from a particular volcano in cubic meters. So when we look at this, here's a list of a couple of volcanic eruptions throughout history, okay, and their VEIs going from 0 to 8. So if we're looking here, you have your typical Kilauea daily eruption that happens, a VEI of 0, okay, and there's how high the material that comes out of it. There's the volume of material that comes out, so about 1,000 cubic meters. As we work our way up, okay, here we have some of the more powerful eruptions. Nevada de Ruiz, which is one of the ones we talked about here. Mount St. Helens, which is right here, is a 5. Okay, Krakatoa, which is one of the loudest sounds ever heard by humans in particularly recent history, which happened in 1883. Okay, Tambora, which is one of the biggest eruptions that we have seen as a species as well. And then we have the Yellowstone supervolcano, okay, which would be one of the most energetic events. And once again, you see here's the plume heights and here's the amount of material that comes out of them. To give you an idea of what we're talking about when we talk about a cubic meter, cubic meter basically you're talking about a box that's a meter on each side, so a cube. So to the Americans, about 3.3 feet here, 3.3 feet here, 3.3 feet. So we're talking about thousands of cubic meters. Think about thousands of these boxes coming off. So if we look at this, okay, here we have an example of some of the 20th centuries or 19th century eruptions and what they have. So here we have Mount Pinatubo in 1991. Okay, to give you an idea, here's Mount St. Helens. Okay, here is the eruption in Alaska in 1912. So there's your plume height and there's your particular amount of ejected material. There's Mount Tambora in 1815, Mount Krakatoa in 1883, and then these are some of the bigger ones that we'll talk about. So here we have Yellowstone's 3 eruptions here, one of the bigger ones here. Okay, Long Valley in California. Okay, compare these to this. You're talking some pretty big, massive, huge eruptions that you are discussing in this case. So when we look at eruptions, we have to realize that they're not exactly the same. They are different in the size of the plume height, like we've seen in the last scale. They're different in the size of the amount of material that's removed. So we categorize them as what we call effusive eruptions for the lightest on the VEI scale, Strombolian, Plinian, and ultraplinian. Now these are all going to differ once again, like I said, in plume height and particularly in the amount of material that is released. The first type of eruption that we're going to talk about is what we call a fissure eruption. So a fissure eruption is a type of effusive eruption, but it's a slightly different one. Instead of having like a towering mountain and having the open vent at the top where it all comes out at, what you basically have is a long crack, and the basaltic lava that comes out of it kind of slowly oozes out. Now you might get some gases released, you might have some slight explosivity, but you typically will have is a long chain and a lot of lava just kind of oozing its way out and spreading out along a long area. And so what you have here is like what you see in this image right here. You have a fissure that runs along here. Okay, you get some lava fountaining out, obviously because of the differences in pressure, and the lava kind of oozes out and spreads out along the ground here. And so you get these wide swaths of land that are going to produce a fissure eruption. Okay, and it can happen because of a lot of different reasons. You might have a pre-existing thin spot in the crust. Okay, you might get some decompression melting, the manta plume comes out, it just kind of finds the weak spots and it just kind of erupts out of the particular land. And so what you'll get is this long chain of lava fountains like you see here. Okay, and it just kind of oozes its way out. You see this a lot of times in different rift valleys and places like that. For example, in the Great African Rift Valley in Africa, in Iceland, you will see this along the mid-ocean ridges a lot of times, the East Pacific Rise and places like that. And so typically what will happen is it'll erupt like this, the lava will come out, and then eventually as time goes on, you'll just get some outgassing, and you'll get these massive lava plains that you'll just see forming here. Now, this has actually happened here in the continental United States. We had these flood eruptions that occurred in the Grand Canyon. If you go to the Grand Canyon to this day, you can actually see these massive flood basalts. You can see how they poured over the sides of the canyon. So imagine what that looked like when it actually happened. You would have had like lava waterfalls cascading down the sides of the Grand Canyon. Would have been quite impressive. One of the largest eruptions to ever occur actually happened in Siberia, in what's today known as the Siberian Traps, and this happened at the end of the Permian period. Okay, almost 300 million years ago, and it may have led to one of the largest extinction events that ever happened on the planet, an event known as the Great Dying. Check out our geological history video when it comes out. We're going to definitely discuss how this eruption led to those sort of events occurring. Now, the next type of eruption we're going to talk about occurs when you have a shield volcano. Now, typically, when you have a shield volcano, you're going to get a effusive basaltic eruption. So this would be what you typically are going to get in places like Hawaii and places like that. And a shield volcano is named that way because it kind of looks like a warrior shield. It has a little bit of a pitch to it in the middle, but it basically has a gentle slope on either end. Okay, and typically these volcanoes are going to form most oceanic islands near subduction zones. Okay, you might get some hot spots also that form this, for example, like you do in Hawaii. So here, for example, you have an example of a shield volcano. So you see how it has a gentle slope. It's very wide. It's very gentle sloping. It's not sharp, steep incline. Okay, if you look at the volcanoes of the island of Hawaii, you could actually see Mauna Loa, for example, here. Okay, Kilauea and some of the other volcanoes, they have this gentle slope here. Okay, they'll tend to have the vent over here, which may or may not have collapsed, forming what we call a caldera. Okay, and it will form this gentle sloping sort of huge volcano, but it will form a shield volcano. If you ever get a chance to go to Hawaii, once again, place I'd love to go, you can go to Volcano National Park. It's a park maintained by obviously the United States government, and you can actually go and tour an active volcanic site and see these things depending on when it is and how it is and what time of year and what's going on. It depends on how close you can get. But you can tour the active volcanoes that are currently still forming this island and making it actually slightly bigger and bigger every single day. You can walk upon, if it's relatively safe, relatively new volcanic rock. So you see these individuals walking across an asphalt road that was covered in what appears to be a pahoehoe lava flow. Obviously, it's dark rock, so it's probably basalt, something you've learned about over and over and over again. Okay. The next type of volcano is what we call a cinder cone volcano. Cinder cone volcanoes are made up from pyroclastic materials. So basically what happens is a volcanic vent erupts, it explodes, little cinders and ash pile up, it goes off again, they pile up, it goes off again, they pile up, it goes off again, they pile up. They tend to be quite steep. Okay, they have 30 or 40 degree incline, and they tend not to live very long. They tend to have a short-lived cycle, maybe one or two eruptive cycles. Okay, and they can pop up in chains as the lava drifts, or as a large magma chamber finds different holes, it'll form slightly different ones. Typically, this will do what we call Strombolian style eruptions, where it might release large amounts of gas. It might make like explosive noises for a while, but it doesn't tend to go on very long. Stromboli being kind of the exception, which has been going on for a relatively long amount of time in the Mediterranean island of Sicily. Okay, and so what you'll typically get is something like this. So here's your central vent. Okay, and what basically happens is it emits all these pyroclastic materials, and so you get this big pile of pyroclastic material building up the volcanic cone. Okay, and so you'll get this in places like Nicaragua, where you have Cerro Negro, which is a volcanic mountain here. There's your vent, and you can see clearly how this is made up of piles and piles and piles of tephra. Here is Cerro Negro on the side, and you can see all the different volcanic blocks and material that would build up this. And this has actually led to a very interesting tourist attraction where you can go volcanic sledding, where you can actually climb to the tops of these volcanoes with a wooden sled, and you can slide your way all the way down. If you go to like Nicaragua and several cities in Central America, you can actually, do this for fun with a bunch of friends of yours, and you can put it on the gram and make a heck of a lot of images and make your friends jealous that you got to do something really cool and really unique. Composite cones are going to be a mixture of these two. So a composite cone, which are typically going to be what you would find in volcanoes in like the Cascade region of the United States and stuff like that, are going to be a mixture of lava flows and pyroclastics. So you can have lava flows, pyroclastics stacked on top of each other, which is why we call it a composite cone. One of the most famous examples of a composite cone would be this mountain, arguably one of the most famous mountains in the world, which would be Mount Fuji in Japan. Okay, it's a mixture of of both pyroclastic and lava flows. It's incredibly picturesque, and because it is the typical image of what you think of as a mountain. It's got that nice mountainous image. Okay, another example would be this right here. This is Mount Vesuvius. Mount Vesuvius located just to the south of Napoli in Italy. This was the volcano which obviously led to the destruction of Herculaneum and Pompeii, which we discussed earlier when we talked about pyroclastic flows. Okay, and like we said, you tend to find these a lot around the Ring of Fire. These are going to be your typical, very explosive, very powerful eruptions that we tend to see a lot of times. So this is an image of volcanic chains in northern Alaska, and so this is going to be what you think of when you see like a volcanic image when you think of it in a movie. Sometimes these composite volcanoes can be, or what we call stratovolcanoes. Sometimes you hear that term as well. Okay, these can be incredibly energetic. There tends to be a lot of material that's released from them. They tend to have a lot of volatiles in them, and they can be very violent eruptions. When they erupt, they can send their plumes way up into the sky. So here you see the plume getting ejected from this, going very, very high up. You can see the blast wave that was released by there clearing this out. And so this can be, quite a dramatic event that can happen. Sometimes when you get a volcanic eruption, you can get what's called a lava dome form. A lava dome is formed when you get viscous magma. Remember, viscous means super, super thick. When viscous magma gets erupted effusively, so it kind of like oozes its way out onto the surface, and then it starts to pile up. So what will happen is basically you'll get lava that comes out of a vent, and it'll pile up as it cools. And what it'll basically do is it'll make a plug inside the main vent. Problem with that is it's kind of like taking a champagne bottle, putting the cork in it and holding it down and then continuously shaking it. That pressure is going to build and build and build and build. And the problem that can happen is eventually that pressure's got to go somewhere. And what can actually happen is a lateral eruption. So what does that mean? It means the volcano explodes out to the side. Okay, and so here you have a lava dome, and literally it looks like a cork inside this crater. So this was lava that got erupted around here, and it just kind of corked the top of this particular volcano. Now that's going to be a huge problem because that pressure and that energy's got to go somewhere. One of the biggest examples or best examples of a lava dome happened in 1980 in Washington State here in the United States. You had this mountain that was called Mount St. Helens. It was affectionately referred to as the Mount Fuji of North America. Very pretty, very picturesque, had a lake in front of it called Crystal Lake, all these really beautiful things. And in May of 1980, it went from looking like this to looking like this. And the reason why was because a lava dome formed at the top, corked the mountain, and a massive lateral eruption happened, which is what you're actually seeing in this image here, blowing this material out sideways. And the mountain lost a couple 100 feet from the top, and it went from that very picturesque image that we just saw to today looking like this. So you can literally see it laterally exploded out this way, and all this material got ejected along this path. And effectively what happened was this. It slumped down, you had a massive eruption try to work its way through the top, and then it just blasted its way out through the side. Thankfully, we were aware of what was going on, that something was going to happen, and we managed to evacuate most of the people around. There were only a few individuals that unfortunately perished. One of them was a geologist, a volcanologist that was studying it, and there were a couple of people who were unwilling to leave their homes. So this is kind of a reminder, if the government tells you something bad is going to happen geologically in the area that you live in, you might want to listen to it. One of the words that I've used a lot during this lesson has been this word caldera, typically what we refer to as a shield caldera. And what basically happens with this is you get a volcano that slowly starts to run out of lava. And as you run out of lava, or specifically magma, as the magma chamber empties, the weight of the material above the magma chamber becomes too much for that particular magma chamber to support. And so what will basically happen is that as that lava gets drained, the crater collapses in on itself. And when that crater collapses in on itself, it creates this large opening with very, very nearly vertical walls um, that shows you the opening of like the magma chamber, or at least a portion of the magma chamber. Okay, now this can happen in a lot of volcanoes, and it tends, like I said, to happen in shield volcanoes. So, for example, if you look at many of the volcanoes in Hawaii and places like that, you'll get this kind of appearance. So here you can see how it kind of has collapsed down, and you probably had a lava lake, and that has since solidified. If you go to Hawaii and you go to the volcanoes in Hawaii, you can actually see the calderas. You can't usually get that close, but you can see how it's collapsed, and you see how it has these nearly vertical walls. Sometimes, if there still is some magma in the chamber, you can get a lava lake that forms. Here you have an active lava lake right there that will form in the center of that. And so that still shows you that there is still some volcanic activity that is occurring. Now, sometimes you can get a lake that actually forms in a caldera. We saw this with Lake Nyos, and we see this in many other places. Sometimes you get a large eruption that basically empties almost all of the magma chamber of a particular eruption. When that happens and all that material gets blasted out, the volcano can no longer support itself. And so what basically happens is the magma chamber collapses, the composite cone collapses, and you get this mountain that was maybe a couple hundred, 1,000 feet that loses a large chunk of its material. And what you'll get is this huge depression. Now, as time goes on and you get sort of weather events that happen, that caldera can get filled in with water, and you can create this enormous lake. Example of this would be Crater Lake in Oregon in the United States. Around 600,000 years ago, you had a mountain there that we refer to now as Mount Mazama. It was an incredibly violent eruption as described by the people who were living there at the time. The native peoples of this region describe a massive event that happened there, that the mountain exploded. And so what you basically see is the mountain explodes, and you see the empty magma chamber right here. See all this empty space. All this weight was kind of resting on this void. Since all this weight was resting on this void, what's going to happen is all this weight is going to collapse down. Gravity always wins. And so what will happen is it collapses in on itself, and you get this massive crater forming. Now, as time goes on, water, rain, snow, all these things are going to fill in this lake. And today, if you look at it, it looks like this. It's actually pretty a beautiful place that you can go visit, Crater Lake. There's hotels around here. You can go boating. You can go do all sorts of water sports. There's actually a little island that you can go to that's called Wizard Island, and it's a very picturesque place that you can go and stay at. It looks absolutely amazing. The final type of volcanic eruption I want to talk about is a supervolcanic eruption. I'm sure you've heard about these things, a lot of scary stuff out there. So what are we talking about? We're talking about an eruption that has a VEI between 7 and 8. Typically, we're looking at an 8. One of the issues that we have with supervolcanoes that makes them very difficult to understand, and they're on the kind of the edge of science right now, is that the edges of a volcano are kind of, the volcano that we're talking about is kind of weird to understand, and they're very poorly defined. We have discovered several of these supervolcanoes that exist around the world. Luckily, none of them has gone off in quite a long time, but we have discovered several of them. Unfortunately, some of them exist here in our own backyard. For example, we have the Yellowstone supervolcano, which exists in Yellowstone National Park. We also have the Long Valley supervolcano, which exists in California. We have Mount Toba, which is in Indonesia, which is one of the most violent eruptions and may have led to a genetic bottleneck which almost wiped out our species a couple thousand years ago. And so when we look at a supervolcano, this is what it would look like if you could see one from a distance. You wouldn't have one particular vent, you'd have several vents. And you would have an enormous amount of material getting blasted into the atmosphere. And when we talk about enormous, this is enough material to get sent into the atmosphere to change global climate patterns. Okay, if Yellowstone was to go off today, we would feel it everywhere in the United States, even on the east coast of the United States. You would get some ashfall occurring even here. Okay, in the middle of the country, it would devastate crops, lives, and everything. And even on the East Coast, it would cause temperatures to drop and all sorts of global catastrophes to food and all sorts of issues. When we look at Yellowstone National Park, what you're looking at here All the different colors represent different calderas and different eruptions that have happened in the past and the extent of them. So you have smaller eruptions which existed here, you have this larger pinker eruption here, and then you have a large older eruption that happened all the way out here. Yellowstone National Park basically sits on an enormous magma chamber on a hot spot in the middle of the North American plate. So much material is exuded out of those that it actually creates these massive walls of welded tuff and other volcanic tephra. And there's a person to scale. All of this was erupted during one particular volcanic eruption. Okay. One of the largest eruptions, like we said, exists in what we today refer to as Lake Toba, but this was a massive, massive supervolcano that erupted, and it released so much material that it caused huge amounts of extinction to occur across the planet, and it may have cut our human population down to a very, very small breeding group, which almost put us extinct several thousand years ago. We can actually see this genetic bottleneck in our genes when we look at our DNA and we examine it. So it's a very interesting event. Now, there's lots of stuff on supervolcanoes. I wish I could spend a lot of time on it, but it's not a whole lot of the curriculum in a lot of schools. If this channel becomes successful and you know, you guys ask for it, I would more than willingly love to do a whole video just on it. But for now, we're going to leave it at that. Finally, when we talk about volcanic activity around the world, like we started talking about what's going on today, when we look at the volcanoes around the planet, most of the volcanic activity is situated around the edges of the oceans. We didn't know what that was for a long time, but once we came up with the idea of plate tectonics, the theory of plate tectonics, it made a heck of a lot of sense. Okay, and so what we've discovered is that there's two main belts of volcanic activity that exist on the planet. There's the belt that goes around the Mediterranean Ocean, and there's a belt that goes around the Pacific, which we refer to usually as the Ring of Fire. There are other places where volcanic activity exists. Okay, you have rift valleys, for example, like the ones in Africa. Okay, you have hot spots, for example, like the ones in Hawaii. You have other rifts that exist, for example, Iceland and places like that. And then you occasionally just have a weird one that'll occur, which would usually be some sort of a hotspot poking its way up. But if we look at the map in general, what you typically will get is most of our volcanic activity occurs around this area, which is what we refer to as the Ring of Fire, although you do have a lot of it occurring right here in Indonesia. And the reason why is you have a lot of plates colliding and converging and subducting and going one underneath the other and creating a very volatile situation. So all of this basically leads us to realizing that the volcanic activity that we're looking at is going to be caused by a lot of different effects and things going on. The main thing being this movement of these large slabs of rock, which we refer to as plates. So that'll lead us to our next topic, which will be plate tectonics.